One of the major controlling factors in the distribution of these deposits is the terrain. We normally think that the glaciers shaped the terrain, and that's true. I don't want to dispel that as a general principle that we can hang our hat on. However, along the edge of the ice, in a terrain as rugged as central New York, the rugged nature of the topography influenced the shape of the edge of the ice and therefore influenced the location in which the deposits accumulated. In the bottom of this diagram, you see a lobe of ice, familiar from a previous slide. And the white spots represent the moraines. The fine stippled pattern represents the outwash. As long as the lobes extended across the valley and was sitting in the valley like this, the distribution of those deposits will be as we see them here. But because the terrain is highly variable in the direction of valleys, and yet the ice retreats in one direction mainly, the ice sheet can be draped across the valleys in various orientations to distribute those deposits in a variety of places. In order to make interpretations about what the stratigraphy is at depth, what the nature of the deposits are at depth, we have to first understand what controls the distribution of the landforms at the surface, and then postulate what happens at depth. We can't predict that with any degree of certainty beyond saying we have hypotheses about what might lie at depth, or we have interpretations of what might lie at depth. These interpretations are based in part on well data that currently exists and we can relate to the landscape. In 1982, the U.S. Geological Survey, in cooperation with the New York State Department of Environmental Conservation, published a paper by two authors who have become well known for the contents of that publication. The McNish-Randall publication of 1982 includes a series of diagrams that look like this. I'll show you several of them. From this, we can then begin to add some details. These are generalizations about geologic settings in which groundwater occurs. The parts of this diagram are bedrock in which the valley is cut, and then the valley is filled with a variety of glacial meltwater deposits. In the legend, you see sand and gravel indicated, and then a different pattern representing lake deposits of silt, sand, and clay. Other important aspects of the diagram is the pattern for bedrock, with fractures existing within the bedrock. And then finally, the last two are shaded patterns to indicate where you can expect high yield of groundwater and where you can expect low yield. You'll notice that all of the lighter patterns are superimposed on the bedrock surfaces. And we can therefore conclude from this that wells drilled in bedrock will create low yield. Low yield being something on the order of possibly 2,000 gallons a day, pumping at less than 10 gallons a minute. That's fine for domestic use. It might be fine for farm use if holding tanks can be developed. But it certainly isn't the kind of material that we would classify as primary or principal aquifer material. That is represented by the darker pattern, and you'll notice that all of the darker patterns lie within the fill of the bedrock valley, the fill of glacial origin. This sort of a pattern, both landscape as well as the layers of material at depth, is the product of glaciers that retreat very slowly within valleys. And as they retreat slowly, they deposit in the meltwaters both gravels by streams that float on either side of the valley, as I showed you in an earlier slide, the discharges mainly from the edges of those lobes. That's where the gravel would accumulate. In the central part of the valley, where the water is quieter, the finer sediment settles out. And these are all lake deposits. This is a cross-sectional view from wells in the eastern part of the city of Oneonta. I show you this to indicate, although it may look a little more complicated than necessary, that the generalization of slow retreat of glaciers and the resulting topography and stratigraphy in fact does fit in many places. And from the landscape we can interpret what exists at depth, because we see in a number of places that the wells corroborate that interpretation. The materials that are the highest yield are the gravels, and very often these occur in the terraces on either side of the valley. Can we go back, please? the button furthest toward the back of the projector on the side. Just hit it twice. On the side. It's half the size of your pinky nail. There you go. Hit that again, please. Thank you. These deposits on the side of the valley that form terraces are the places where the best sand and gravel occurs for aggregate material. And it's also the place where the best infiltration will occur of melting snow and rain. So these represent recharge areas for groundwater. In the McNish-Randall diagrams, these are also the places where the greatest amount of groundwater will exist. Well, these deposits were formed into a lake, building as a delta out into a lake. And that's what these inclined layers tell us, that this is part of a delta deposit. And we make the interpretation of the conditions under which these were formed, and therefore can interpret the stratigraphy beneath them. We go on to another diagram that was provided, a generalization that seems to work. When the glaciers retreated very rapidly, the valleys were filled with lakes, much like the modern Finger Lakes, but of much greater extent. Somewhere down valley there had to be a dam, and we're not concerned with that at this time. But we accept the fact that there were major lakes in these valleys because the floor of the valley landscape is that of the floor of a lake, and the layered materials beneath it are those materials that form in a lake: fine sediment, silt, sand, and clay. Interestingly enough, beneath these, at the bottom of this pile, at least half the time, we find confined aquifers, aquifers confined beneath these less permeable, less porous materials of the lake. These finer materials are generally not very aquifers because the spaces between the grains are not very well connected, and we can't pump a lot of water out of it, although there may be a lot of water in it. We need to find the gravel deposits where the spaces are easily connected and the water can be easily pumped. And down here, a confined aquifer such as this would be a very high-yield aquifer. A well through this material and into this could create, has the potential to create 1 million gallons a day, and therefore serve as a primary or principal aquifer. But only half the time do we find that material at the bottom. So it's not the high percentage good aquifer type location. Here's a cross-section from an actual location, Hyde Park being near Cooperstown, and the same stratigraphy shown in the hypothetical diagram is reflected in the actual case. This adds confidence to our interpretations. These are the nature of the deposits that form in the lake. This is grass down here for scale. You get an idea that these layers are just a few centimeters thick each, forming thousands of layers in a thick pile that can be hundreds of feet thick. An individual layer would consist of silt or clay or very, very fine sand. This is not very good aquifer material.